Hello. Yes, so double share. So in double share, the previous examples that we looked at, we had basically one surface. There is one plate connected to another. Mm. There is the angle bar connected to the flange of your column. So the space created is what? Just the space between the angle bar and the what? And the flange of the column. So that's what single shear surface. So in double shear surface, we have two surfaces. For instance, when you have, let's say this is the web of a column and you have one beam to the right and one beam to the left, and you have angle bars, okay, at side and side. So this one is connecting this beam, this one too is connecting this beam. So between this angle bar and the web, we have a bolted connection. Okay. And also between that same web and this angle bar, the bolted connection continues. So we have one bolt that is pinning two beams to the web of a column. So that connection gives us what? Two surfaces, two shear surfaces. That is one, the first one being the shear surface between the angle bar and the web of the column, and the next one also being the what? The shear surface between this angle bar to the right and the web of the column. So that gives us what? A double shear surface. And the failure mode of this double shear surface is also the same as we saw in the previous example where we had single shear. So what it means is that the strength of this connection would be two times that of the previous. So the shear strength that we calculated, we're just going to multiply it by 2 because we have connection between the what? The angle bar to the left and the web, and also between the angle bar to the right and also the web. So that gives us two double shear surfaces, and so the strength will be what? Twice as big. So we can also have our connected parts resisting what? Tensile load. For example, where we have this typical connection, okay, so you have this section below being pulled, okay, and you have this section at the top. So the pulling force would be translated to the tensile force in the connection. So the more they pull, the more the what? The tensile force. So basically the efficiency of the connection will depend on the connected part to resist the tensile load. So here we are looking at the bolts. So the bolts should be able to what? Resist the tensile load that is being applied to them. Again, if you look at, so that's with respect to the bolts. Now if you look at two plates being connected, so this is a single shear surface. You have one being pulled to the right, one to the left. So what it means is that the plate 2 will be in tension. So the integrity of the connection will depend on the ability of the plate to resist the what? The tensile force. So let's see how we will be able to quantify the tensile resistance of the bolts and the tensile resistance of the plates. So for the bolts, this is what the code gives. The nominal tension capacity is given as this 0.8 pt, where pt is the tension capacity of the bolts. Okay, so that one too, the pt, the tension capacity or the tension strength of the bolt, that one also is given in the code in table what 34, so you can look at that. And then 80 is the tensile stress area of the bolt. So pt, let's see it in the code. So we have the tension strength of the bolt in table 34. So depending on the grade of steel, we have the respective tension strengths of the bolt. So with respect to the plate, the tensile capacity is given as this expression, where AE is the effective net area of the plate. So the effective net area basically is you know effective area of the plate after taking the holes. We understand that after drilling holes in a plate, its ability to resist tensile forces would be less. Okay, so just take a complete plate, or let's say a paper, try to pull it, and then in the next step, take that same paper, just punch a hole in it and try to pull it. Which one would be easily torn apart? You'd see that the paper with the hole in it would easily be torn apart. So that's the concept here. So the effective net area takes care of those holes, and that is given by this expression. Yeah, where K is a coefficient in the code, AN is the net area, and AG is the gross area of the plate. So K is basically 1.2 for grade S275 steel, and we have other values given in the code for various types of steel grades. So in an instance where we have uh, combined shear and tension being applied to a connection, as we have here, okay, you see, once the load is applied, so it tries to push this bracket down. So it means that basically the connection here will be in shear. Okay, so now if we take here as the center of rotation, and again this force is applied, and in trying to pull this apart, so this bracket would try to move out in this direction, in the right direction. So it means that we are having a bit of rotation here. So each of the bolts would be pulled. Okay, so and being pulled means that the bolts will be in tension. So once we have such a connection where we have shear and tension combined, what we need to do is to check the shear and tension resistance, okay, of the bolts, of the bolted connection first. Then we move on to check this relationship and to ensure that it is satisfied. Okay, okay. So where Fs is your what? The applied shear force. Ft is the tensile force, and the Ps is your shear capacity, and this is the nominal tensile capacity. So once you compute all of them, you just insert them here to ensure that they are less than 1.4.